Good evening, Year 12s. I got home this afternoon and went for a run, and halfway around the block it occurred to me that we haven't had a video for a while. So I thought to myself, well, it's time I rectified that situation. So here we are with a video on buffers, which we're covering as part of our learning on acids and bases. So guys, to start, what is a buffer? Well, it's a system or solution that has the ability to resist change in pH. So ordinarily, if you just had any type of solution or system and you added an acid to it, so for example, you added some hydronium ions, then ordinarily the pH would decrease. And on the flip side, if you had a basic solution and you're adding hydroxide ions, then the pH would increase. The beautiful thing about buffers is that they have the ability to consume what it is that you've added and resist any changing pH. And Le Chatelier's principle will play a big role here with how buffers actually have the ability to work. So, if I can get my background right, essentially, guys, there are two types of buffers. You can have acidic buffers or you can have alkaline buffers. So I'll start with acidic buffers, and basically there'll be a solution that has got a pH of less than 7. Obviously, that's the very definition of an acid. And acidic buffers are generally made of a weak acid and it's salt. So, for example, the most common one we've got is acetic acid, and its salt's sodium acetate. Now, the reaction that you would draw up for an acidic buffer of acetic acid looks like this: our standard CH3COOH plus water, and we need double arrows in there. And then we've got CH3COO minus, which is our acetate ion, and we're dealing with an acid here, so we've got to put in some hydronium ions there as well. So guys, in order to make an acetic acid buffer solution, you would take some acetic acid and you would also then dissolve some, we can say sodium acetate or potassium acetate into it, and that's where we get these acetate ions from. So a solution of this acetic acid buffer contains many acetic acid molecules, because remember, it's a weak acid, so it doesn't ionize very much. So we've got lots of these molecules in here. We've also got lots of acetate ions in here because we have dissolved sodium acetate in here. So we generate a lot of these ions from the sodium acetate. I'll just put here from, in brackets, from the sodium acetate. So that's where we get these acetate ions from. You do not need a minus sign there. And we don't have many, but we've got enough hydronium ions here, which get generated from the ionization of the acetic acid. We've got enough of them to give us a pH of less than 7. So in fact, the pH of this acetic acid buffer solution usually sits at around about 4.8. You guys don't need to concern yourself too much with that value, but just be aware that it is acidic. Okay, so this is the setup of the buffer system. Now, if you added some acid to this system, what would happen? How does it resist a change in pH? Well, if we add an acid, we are essentially adding hydronium ions, yes? You are adding them to the system. Well, look where we've got some hydronium ions here on the right-hand side. So by adding an acid to this system, we are adding something here on the product side. So we are, scribble that out, we're increasing the concentration of hydronium ions. in which case the equilibrium is going to shift left in order to consume these ions that you've added, these hydronium ions. By consuming them and pushing the equilibrium left, you are removing these hydronium ions from the system, and you are therefore maintaining the same pH. Once they're removed, they can't have any role in altering the pH. So that's what would happen if you added an acidic solution. If you added a basic solution, so we're now going to be dealing with adding hydroxide ions to the solution, then your hydroxide ions would react with these hydronium ions here in what is a simple neutralization equation. Okay, H3O plus, and hydroxide is a neutralization equation. It's just going to yield water. Two of them, in fact, if we're going to be specific. So you add a basic solution, you remove those hydroxide ions by reacting them with hydronium. If you are reacting these hydronium ions, then essentially you are actually decreasing their concentration. So in order to replace them, you have to shift the equilibrium right. Okay, that's Le Chatelier's principle coming into play there. One thing that your textbook doesn't mention, but that I think is worth noting, and we'll pick up a colour change for that, is the addition of any hydroxide ions can also react here with the acetic acid molecule, and that reaction would then yield the acetate ion and water. So that's another way in which the hydroxide ions can actually be removed, right, is to react them with these whole molecules of acetic acid. So guys, that's an intro to the acetic acid buffer. I now want to talk a little bit about a basic buffer, and obviously the very definition of a base is going to mean that it's got a pH of more than 7. So alkaline or basic buffers, there's not many examples of alkaline buffers, but the most common one is the ammonia buffer. So guys, that has to, the alkaline buffers, just like the acidic buffers, they have to be made of something weak. So in this case, for an alkaline buffer, we need a weak base and its salt. So the ammonia buffer is made with ammonia and often something like ammonium chloride, for example. So that's its salt. So its setup looks something like this: NH3 plus water, double arrows, because remember we're dealing with something that's a weak base here, so we've got to have those double arrows in. And we've got NH4 and hydroxide ions. Okay. So guys, the ammonia here comes from our ammonia, and our ammonium ions come from the salt here that we're using. Guys, just as the sodium in the sodium acetate didn't play a role in the acidic buffer, the chloride here has no role in this buffer either. It's the ammonium ions that we're interested in this situation. So it's important to recognise that in this buffer system, because it's a weak base, we've got lots of these NH3 whole molecules. Okay, they don't ionise very well, so there's lots of them. We've also got lots of ammonium ions because we've dissolved this ammonium chloride salt in this solution. And we've got a few but not many hydroxide ions, which lead us to have a pH of greater than 7. In fact, for this setup, the pH sits at approximately 9, so it's slightly alkaline. If you added a base to this system, so we took some base, therefore we've added hydroxide ions, then it seems fairly logical that an addition of these increases the concentration of hydroxide ions that we've got on the right hand side of the equation. In order to remove those added ions, you react them with the ammonium ion. So you shift your equilibrium left in order to consume them and maintain a neutral pH. Well, sorry, maintain a pH that remains at 9. If you added if you added an acid to this system, so hydronium ions, then you react these hydronium ions with the hydroxide ions here in a neutralization equation, very similar to the setup that happens in the acid. So you remove them by reacting these. If you start reacting the hydroxide ions that you've got, you decrease their concentration. Le Chatelier's principle, you're going to shift that equilibrium right in order to replace the ones that you've just removed. Guys, also not mentioned in your textbook, but again, totally worth noting, is that the addition of an acid, so these hydronium ions, can also be dealt with by reacting them with the whole ammonium molecule here. So that reaction would look like this. You've got your whole ammonia molecule there reacting with your hydronium ion or ions, and that will yield NH4 plus and water. So that's another way that this system can contend with the addition of an acid. Guys, just to give you a quick introduction, you'll read more about this in your text and in class, but perhaps the most important buffer system that we're going to discuss is the buffering of human blood. So, guys, blood in the body, in humans, the pH has to be maintained between 7.35 and 7.45. So it's very slightly alkaline. Now, note this, there is not much room for movement here. So the blood has to be able to contend with the addition of either hydronium ions or hydroxide ions, and it has to be able to consume those and maintain a pH that's between these two ranges here. So guys, that is the carbonic acid, which is our our H2CO3, which we all know is a weak acid, and our bicarbonate ion. So that is the primary buffer system for blood. We've also got some hydrogen phosphate that plays a role in maintaining the appropriate pH for the blood in humans. So, guys, that's a very brief introduction to buffers, and we'll be doing an experiment on Thursday and Friday on buffers and how they can contend with the addition of hydronium and hydroxide ions. Thank you very much for listening, and I'll see you next time. Happy study.